Hello everybody, in this video we are gonna prove Squeeze Theorem, and I will explain the statement of Squeeze Theorem as well as the proof itself. So just keep watching the video if you're interested in that. And yeah, don't forget to enter in the giveaway. Check out the description box below for the rules. Please subscribe to make sure your maths teacher never gets mad at you. Okay, first look into the statement. We have three sequences of real numbers x, y, and z. And we suppose that they are having two relationships between them. The first one is that xn is less than or equal to yn, which is less than or equal to zn for all n belongs to natural number. Now what does that mean? So this means that all the corresponding elements of xn remain less than or equal to all the corresponding terms of yn, which would always remain less than or equal to all the corresponding elements of zn. By that I mean, for instance, x100 maybe is less than or equal to y100, which is less than or equal to z100. So the corresponding elements of all these sequences remain in this kind of relationship. And by x100, y100, z100, I mean the specific terms of these sequences. Alright. Now the second relationship that these sequences have is that the limit of xn and the limit of zn is same. Now what we have to prove is that y equals to yn is convergent, which means y is also approaching to a specific limit, and that limit is also equal to the limit of xn and zn. So we have two suppositions that xn is less than or equal to yn, which is less than or equal to zn, and the limit of xn and zn are equal. So we will take these two suppositions and we will prove that yn is convergent and the limit of yn is also equal to the limit of xn and zn. So that's the statement. Now let's move on to the proof. Alright, on to the proof. We are going to take the second supposition that we have, that the limit of xn is equal to the limit of zn, and we are going to suppose that omega is basically their limit. Alright, so now we have to discuss the definition of limit so that we can further move on to the proof. Now the definition of limit is a sequence an is said to have a limit a if for any epsilon greater than 0 there exists n naught belongs to the natural number such that the distance between the sequence and its limit is always less than epsilon for all n greater than or equal to n naught. So this is the definition of the limit, and now we are going to apply this definition onto the limit of these two sequences xn and zn. Now, by definition of limit, we can say that the distance between xn and omega is always less than epsilon for all n greater than or equal to n naught, because omega is the limit of xn. Same goes for zn. Now, using the first condition or hypothesis, that is xn is less than or equal to yn, which is less than or equal to zn for all n belongs to the natural numbers, we can say that xn minus omega is less than or equal to yn minus omega, which is less than or equal to zn minus omega. So we are not disturbing the inequality here. We are just subtracting omega from all these sequences to proceed further in the proof. We just need to keep in mind our goal, which is to prove that yn approaches to omega. So for that, we're going to take the left hand side of the inequality we just discussed, which is xn minus omega is less than or equal to yn minus omega for all n greater than or equal to n naught. We also know that mod of xn minus omega is less than epsilon for all n greater than or equal to n naught. Now, I want to remind you of a rule that you have already learned, that for absolute value of a real number a greater than 0, mod of x is less than a if and only if minus a is less than x, which is less than a, where x is a variable and a is greater than 0. So I'm going to apply this rule of absolute value on the absolute of xn minus omega to get this. So we got minus epsilon is less than xn minus omega, which is less than epsilon, as we know that epsilon is greater than 0, and this is true for all n greater than or equal to n naught. So here we just applied the rule of absolute values on the mod of xn minus omega, and we are going to do the same exact thing on mod of zn minus omega less than epsilon. Now, by combining these two inequalities, we get a new inequality, that is minus epsilon is less than xn minus omega, which is less than or equal to yn minus omega. And this implies that minus epsilon is less than or equal to yn minus omega for all n greater than or equal to n naught, and then we save it as our first inequality. Now I want to remind you the same exact rule of absolute value of real numbers, because we're going to use it again. So taking the right hand side of the inequality, we have yn minus omega is less than or equal to zn minus omega for all n greater than or equal to n naught, and also we know that mod of zn minus omega is less than epsilon for all n greater than or equal to n naught. So we are just going to apply the rule of absolute values of real number onto the absolute of Zn minus omega, and we get that minus epsilon is less than Zn minus omega, which is less than epsilon. Now by combining the right hand side of the inequality with this new inequality, we get yn minus omega is less than or equal to Zn minus omega, which is less tyn epsilon, which implies that yn minus omega is less than epsilon for all n greater than or equal to n naught, and we will save it as our second inequality. Now by combining the first and second inequalities, we get minus epsilon is less than yn minus omega, which is less than epsilon for all n greater than or equal to n naught. Do you remember the rule I told you earlier about absolute values? Yeah, this one right here. We can apply this rule, the same exact rule, on the inequality that we just created, because it works both ways. Now we can say that mod of yn minus omega is less than epsilon for all n greater than or equal to n naught. Wow, we have reached to the end now. So this implies that omega is the limit of yn, and this implies that the limit of yn is equal to the limit of xn and to the limit of zn. And as omega is the limit of yn, so this proves that yn is a convergent sequence. So that's all that we need to prove. So we have finally proved both of the conditions, and I think that's it. So thank you so much for watching this video. I will see you guys all in my next one. Please subscribe and take care.